So inverses of square matrices in the n by n matrix, so 2 by 2, 3 by 3, 4 by 4, is often referred to as a square matrix, as the number of rows is the same as columns. The order of this square matrix is n. A square matrix with ones in the diagonal and zeros everywhere else is referred to as the identity matrix and is denoted by that I. This matrix is often called the multiplicative identity for a comparable matrix. Now, why would that be true? Well, just to show you why, if I take some other matrix over here, 1, 2, 3, 4, for instance, and multiply it by that identity matrix, take the first row times the first column, I get 1. The first row times the second column, I get 2. Second row times first column, I get 3, and same with 4. The reason they call it an identity matrix, just like the multiplicative identity is 1, the identity matrix gives you back what you multiplied, what you started with. This matrix is often called the identity matrix, so A times I is equal to I times A, so it works in both directions, which is not true for most of the multiplication. It's not commutative, but with the identity matrix it is. These also are useful for finding inverses. If matrix A is invertible, non-singular, that means you can find an inverse. Singular means, down here we talk about the matrix is said to be singular. For a matrix without an inverse is called singular. That we can find, so if we can multiply this direction and multiply that direction, and you get this identity matrix both ways, then we know that you can find they are inverses of each other. So the first method that we're going to use for finding this inverse is we're going to say, hey, we know that if we multiply A times B, we're going to get an inverse. So if I start out by taking first row times first column, I get 3x plus z, and then I'm going to take first row times second column, which gives me 3y plus w. Second row times first column gives me 5x plus 2z. And second row times second column gives me 5y plus 2w. Well, I know this has to be equal to this identity matrix, so I'm going to make my system of equations 3x plus z is equal to 1, and I'm going to take the first, we got 3y plus w equals 0, and I'm going to rewrite the other one over here, so 5x plus 2z is equal to 0, and I get 5y plus 2w is equal to 1. Well, if I solve these equations, let me see here. Let's just solve for one of them, then I can just give you the others. Let's say I have 5x is plus 2. Now if I solve this one for z, instead of writing z here, I can write 2 times 1 minus 3x is equal to 0. And solving that, I get that I get negative x, because 5 minus 6, and then it looks like a plus 2 equals 0, so x is equal to 2. And I can do the same for the rest of them and end up with 2, negative 1, negative 5, 3 as my inverse of this. Now to show that, I'm going to make space down here and multiply 3, 1, 5, 2 times 2, negative 1, negative 5, 3. And if I do that, I get 6 minus 5 gives me 1. And top row, second column gives me negative 3 plus 3 is 0. Second row, second column gives me 10 and negative 10. And second row, second column gives me negative 5 and positive 6. So I get the identity matrix when I multiply them. All right. And a slightly shorter procedural explanation: attach a n by n identity matrix to the right side of a matrix and use the row operations to get the identity matrix on the left side. So what they're saying there is if I take my original matrix, 3, 1, 5, 2, and I attach an identity matrix, 1, 0, 0, 1, and then I solve it so the identity matrix is on this side, then this side will be the inverse. So let's try to do that. Give myself a little room. First thing that I'm going to do is I'm going to take 2 times row 1 minus row 2, and I'm going to put that back in row 1. So I'm going to get 6 minus 5, and I get 1 there, and I get 2 minus 2 gives me 0, and I get 2 times row 1 gives me a 2 there, and 2 times 0 minus 1 gives me negative 1, and do it again. On the bottom will stay the same. And this time I'm going to get a 0 in that position, I'm going to take row 2, which is that 5 there, minus 5 times row 1, and I'm going to put it back in row 2. When I do that, my top row stays the same, but my bottom row becomes 5 minus 5 is 0, 2 minus 0 gives me 2, and 0 minus 10 gives me negative 10, and 1 plus 5 gives me 6. Then I'm going to, just for the fun of it, I think I'm almost there, I'm going to take my row 2 and I'm going to multiply it by a half, and then I'm going to put that back in row 2. And I'm going to write my answer up here because I'm running out of room. So my first row stays the same, 1, 0, 2, negative 1. My second row, just I get 1, negative 5, 3. And so then this part has become the identity matrix. This is the inverse of the original. So that's a little bit shorter than solving the system of equations, but nonetheless it works. A shortcut for 2 by 2 matrices is to follow this formula. We take 1 over AD minus BC times D negative B negative CA. Well, just for the fun of it, let's put in some matrices, 7, 9, 4, 5. And if I do 1 over 7 times 5 minus 4 times 9, and then I'm going to take D -9, -4, and 7. Switching the position, so this is A, B, C, D. And this ends up being 35 minus 36, so I get 1 over -1 times that switched matrix, which causes all of them to switch to -5, +9, +4, -7. And this is the matrix, is the inverse of this. So if I was to take 7, 9, 4, 5 times its inverse, -5, 9, 4, -7, I would get the identity matrix. You can take your time to show that to yourself. All right, if I consider the system and I want to write the matrix equation in the form AX plus B, which represents the system, now we want to solve for X. So if I have this, we know that anything times its inverse would give me the identity matrix. So I end up with the X is equal to the identity or the inverse times B. So just a little bit of a proof there to show that it happens. And let's see if we can make that happen over here. So my matrix that I start out with here, my original, and we'll call it A, because that's what they're using over here. So I'm going to have 1, 2, 8, 3, 4, 6. And pause. All right, so if we're going to take our A, which is going to be this 1, 2, 3, 4, and we're going to multiply that by this X thing, so we know our variables are X and Y. We're going to get a matrix 8, 6. Okay? Then we have to multiply by the inverse. So let's take some time to find the inverse. So what I'm going to do is I'm going to start out with this 1, 2, 3, 4 times this, and I'm going to solve it. And if I do row 2 minus 3 times row 1 and put that in row 2, and I'm going to pause and do this because I'm going to run out of time. So after doing some work, I ended up with the inverse being -2, 1, 3 halves, -1 half. So that's my inverse. So if we go back over here to where we're solving, I should take this inverse times my B, which we said was these numbers here. So I'm going to take -2, 1, 3 halves, -1 half, times this 8, 6. Now, first of all, is it even possible? This is a 2 by 2, and this is 2 rows and 1 column. So the middle ones are the same, so we are able to. So I'm going to take the first row times the first, well, times the only column, and so I get -16 plus 6. Hope you can see that. -16 plus 6 gives me -10. And if I take -3 halves times 8, gives me 412. And -3, 12 and -3 gives me 9. So I get the matrix -10, 9. Well, that should be left being equal to this xy. Well, if the x is equal to 10, the y is equal to 9. So by using this manipulation, you can get the solution. Now let's talk about